All right, we're going to do the second part of 4.4. So yes, and turn to page 5. Okay, so we have a formula that we're going to talk about. It's called average value theorem. It's basically mean value theorem for integrals. If you kind of recall what mean value theorem did, mean value theorem says if I have a curve and the slope between the endpoints is some value, let's say that slope is 1/2 or 2 or 3. We can guarantee a slope somewhere along that curve, right? Mean value theorem says, okay, if this is slope of 1/2 and the curve is smooth and there are no breaks, there must be some point that also has that same slope. That's what mean value theorem does. It's trying to guarantee a slope. Now with average value theorem, it's trying to guarantee a height. Okay, guarantee a height somewhere along a curve. Let me do some connection here with a formula that we know. What's the area formula for a rectangle? Area of a rectangle is what? Okay, length times width. I'm going to rearrange that wording. It's fine. I just want to rearrange it to be width and height just to make it more visually connecting with what we are going to see. But length times width is fine. Yeah, packet. Yeah. So we know that area of a rectangle is width times height. What if I were to rearrange this equation here? If I asked you to solve for height, how would you solve for height? Height will be equal to what? Okay, area divided by width. Okay, so area divided by the width is equal to the height. Okay, so this makes sense, right? If you know an equation, if I ask you to solve for one variable, you can just rearrange it by dividing it, or dividing one variable and moving it over. Okay, so this is basically what this messy expression is describing. Okay, height is equal to the area divided by the width. Now, let's say I were to pull that width out. Same thing as saying height is equal to 1 over the width times the area. I mean, this is area divided by width, but I just want to show you how this form is coming about. So f of c is basically showing us height. So height of a point on the graph, or the height of the average value I'm looking for, is going to be the area divided by the width. Okay. So here, this is my area component. And the width is just b minus a. Okay. B minus a is just whatever my endpoints are, I'm just subtracting that to get to my width. Right. So b minus a is my width. This is my area. This is just rearranging. I mean, it looks more complicated, but really it's just rearranging the area formula and say, if I want to find the average height across my graph, it's going to be the area divided by the width. Okay. So the big idea here is that, let's say this is the curve, right? If the curve is here, if we were to take this area of a curve or this shape of a curve, and if I were to kind of push down on the curved portion and make it flat, I can always take a curved region and force it into a rectangle that shares the same area, right? So here the statement says, there exists a rectangle such that the area of the rectangle is the same as the area under the curve, and f of c is the height of that rectangle. So basically, if I were to take all these heights across this curve, and if I were to average them out, the average height of between all these points is the average value of my function. Okay, so again, if I were to average out all the points on this curve, the average height is what I'm looking for here. So let's look at example 1. Example 1 says, find the average value of the function from 2 to 5. So in other words, I want to find across all these points, what is the average height amongst all my on the curve, average height on the curve. Okay, so we're going to go through this formula here. So f of c, my average height, is 1 over b minus a times the integral from a to b of f of x. Okay, I'm pulling out the width, but I could write it this way. We don't write it this way because it looks even messier. But I just want to show you that this is the same thing. I'm taking my area, I'm dividing by the width, right? Area divided by width. But rather than making it look that complicated, we typically pull it out as a coefficient. So I want to show you that really it's the same thing. It's just this looks a little bit cleaner, pulling that denominator in front of the integral. Okay, so we're just going to plug everything in as we see. What's our a and b value? 2 and 5. And then my f of x is, yeah, x squared plus 1. So I'm just plugging everything in as I see it. I'm not doing anything calculation-wise. I'm just putting in the parts that matches my formula. So 1 over what? I'm going to take a step before it, but yes, it is 3. Definite integral from lower bound to upper bound 5 of x squared plus 1 dx. Okay, so all I'm doing is I'm just inserting the specific values into my formula. Okay, questions so far? And then what happens to that 5 minus 2? It becomes what? 1/3. Okay, we see a definite integral in front. We see a coefficient. We can, leave that coefficient for later. If you see a definite integral, remember from yesterday, what's the first thing that we do? Not derivative, but the antiderivative, right? Yeah, antiderivative. So we ignore the bounds, right? And again, a lot of students want to do this. They want to start inserting the 2 and 5 into the x squared plus 1, but it's not ready, right? We have to transform, excuse me, we have to transform this x squared plus 1 into the antiderivative before the 2 and 5 plays a role. So I know a lot of students want to plug the 2 and 5 directly in because you read from left to right, and that's your natural tendency. But we're going to take care of that x squared plus 1 first, and then do the 2 and 5, and then from 1 to 3. So it's not backwards, kind of moving from right to left. Okay, so I'm just going to step to the side here. I'm just going to take care of this antiderivative so that I'm not having the bounds kind of getting in the way here. Okay, so what's antiderivative of x squared plus 1? Yeah, x cubed over plus x, okay? Now that I have my antiderivative, I can evaluate. So now I'm going to evaluate between 2 and 5. Right now, I'm still ignoring the 1/3. I don't want to introduce that 1/3 and make it even messier. I mean, you could, it's up to you, but I'm just going to try to remember this to do at the end. Okay, what's next? Yeah, so 5 first, right? Okay, followed by? Minus 2. Yeah, good, minus. So minus big parentheses. So from yesterday, it's uppercase f of b minus uppercase f of a, and my lowercase f for the antiderivative, my integrand is this x squared plus 1, okay? Now, just to speed things up here, rather than having you guys try to do common denominators, all that, this ends up cleaning up to be 126 over 3. But have I finished the problem yet? Is this my average height? I still got to do what with this? Yeah, multiply by 1/3, right? So don't forget, even though most of our work is, we have the area, but we still got to deal with the width, right? Area divided by the width is equal to the height. So we still have to involve that 1/3. So my average height is going to be the width component and the height, my area component. We can use your, let's see, this next. Oh, so your test is going to be non-calculator, but you can leave your answer unsimplified, and I'll accept that. Okay, so basically it won't be as messy as this, but even on the AP exam, you could say 1/3 times this whole thing. Okay, but just for cleanup purposes here, I just want to show you what the average height is. 126 divided by 9 is equal to 14. So that's my average height.
So you're always gonna be looking for the average height in these problems?
I'm sorry?
You're always gonna be looking for an average height.
Well, if the problem says find the average value, then that's the indication. Okay, I'm looking for average height, and I'm going to use average value theorem. Maybe down the line, but on this upcoming test, which is non-calculator, you would just have to work it out by hand. But if you don't clean anything up, it's fine as long as all your work is there. It can be one big mess. I mean, on the test, it won't be as messy as this, but that's the idea, is that you don't have to worry about, oh, I gotta do all this messy adding and subtracting, messy fractions. Okay, you don't have to worry about that. Right. So I want to kind of just go back to the idea of a visual connection between this number and what it tells us about the graph. So this is what the graph looks like, okay? So I want to kind of give you this, because this is going to link up to part B here. This is what the graph looks like. This is x squared plus 1. Okay, x squared plus 1 is a parabola with a y-intercept of 1. So maybe something like this. Now, the interval is only from 2 to 5. So between 2 and 5, if I were to average out all the heights, the average height amongst all these y values is going to be 14. Okay. That's what this is telling us. Okay. Does that make sense? Right. So if I were to take all these individual y values and if I were to average all of them out, the average height amongst this region is going to be 14. Now, this is not completely accurate, but just want to kind of give you something to visually connect with what we're doing abstractly. So now part B is saying, find the C value. It says, basically, we know the average height is 14, but can you tell us where the graph actually hits 14? Now, this is what average value is also guaranteeing. Is it possible to have an average height of 14 without the graph ever hitting the y value of 14? It's impossible, right? So just like mean value theorem for slope, is it possible to have a slope of 1/2 without the graph ever reaching a slope of 1/2? That's impossible. Same thing here. If my average value is 14, I've got to have that 14 live somewhere on the graph. At least once, maybe more than once, but at least once. So then part B is saying, find the C value. Where does the graph actually hit a y value of 14? Again, this is not accurate, but how would you go about finding the x value at this location? Yeah, plug 14 into what? Good, right. If I know what the y value is, I'm just working backwards to figure out where the graph actually has that y value at a specific x. Yeah, so that's exactly it. Okay, we take 14, insert into the height. We know the height. Let's find the location for that x. Okay, so 14 is equal to x squared plus 1. X squared equals 13. Okay, and how do I solve for x? Take the what? Square root. Whenever I take the square root of an equation, what's going to happen as well? What's going to show up? Plus or minus. Now, it says find the C value. Just understand that the C value just means the solution for the x. So I have two C values. So this tells us that the graph actually hits 14 at two different places. Over here and over here. It's a parabola. But do both of them fit into our criteria? No. A negative doesn't, because it's not part of our range, right? Our range is from 2 to 5. So yeah, this extraneous. So C is just going to be root 13. Just like with mean value theorem, whenever you find a C value for mean value theorem, you always have to locate the solution between the bounds. Anything outside the bounds is not part of our problem. So as messy as this process looks, the idea is I'm just trying to figure out what the average height is amongst all the y values on my curve. And then once I find that average value, you may be asked to figure out where the graph actually hits that average value. And you just have to take that y value, insert it into the original equation, and solve for x. Okay, any questions here? Okay, we'll practice with this concept after I introduce the next topic for today, but really you're just plugging into the formula. Okay, take the antiderivative and just remember, keep your just don't get distracted by the bounds, right? I know that some of us will want to insert the bounds in, but keep reminding yourself, I got to take care of the calculus portion before I can work the bounds in. I got to turn this into something else before I can work the balance. And I can't just plug the 2 and 5 into the expression. That's the biggest mistake that students make with average value theorem. They don't do the calculus and they just insert the expression in or value into the expression. Okay, let's go to the next page, page 6.
All these formulas have to be.
Yeah, this is the second theorem. This is a important. This is a important concept, just like first theorem. First theorem is just we take the antiderivative and then we plug in upper and lower bound, right? So we solved different variations of that yesterday. This is called the second fundamental theorem of calculus. So this is a definite integral as a function. So to recap, we know that indefinite general integrals is an area finding function. A definite integral finds the area between two x values. Now, there's also a function that is the integral itself, and that feels a little messy. It's like, well, how do I deal with a function that has an integral in it? So instead of going from a constant to a constant, we're going from a constant to a moving value of x. It's not that important that we have to worry about, oh, I got to worry about all this mess, but just have to know how to deal with that integral notation if it is in the function. So the second theorem says that if I were to apply a derivative and integral operation on the same function, what do you think they're going to do to each other? If they're inverses of each other, yes. So that's the big idea. If I'm doing a derivative of an integral of a function, that function is not going to change much because the derivative and integral operation will just kind of undo each other. Okay, so I want to talk about what that means. So you see how there's an integral of f of t, and there's a derivative of an integral of f of t. These two operations they're gonna cancel each other out. The f of t is not going to change much, but there is going to be some residual effect from these two operations, even though they do cancel each other out. So what's going to happen is they are going to still have some impact. The impact is that the function is not going to change, but the upper bound is going to get inserted into the function. Okay, I just got through saying that we never do that, right? But this does happen because we're taking the integral and we're going backwards. So this bound gets inserted into the function. And the derivative also has an impact. The derivative is going to cause the upper bound to turn into the derivative of that upper bound. So this is a formula that we want to be able to use. So the big idea is that, okay, my function is not going to change much, but these two operations is still going to leave its mark on the answer. Okay. I think I want to go through these examples and then kind of prove to you why this works, because sometimes I feel like if I just go through this is kind of a shortcut method, but if I don't show you the long way, it's hard to appreciate what's happening. So let me go through the rule first, and then I want to show you some examples, like why is this the case, and why do we have to go through this method? Okay. Okay, let's look at example 2 here. It says the derivative of a definite integral of square root of t squared plus 4. We're just going to follow what this rule is saying. Okay, these two operations are going to cancel each other out. We're not going to go through and do the antiderivative. No need to do power rule. All we need to do is plug the upper bound into the function. That's what the expression is saying. So replace every t with x. So what is that going to look like? Square root of what?
X squared plus.
Yeah. Now, we would never do this if it was just an integral, right? I would then say, oh, you got to take the antiderivative, and then you can plug the upper and lower bound. But we have two operations that are undoing each other. That's why we can do this. Times, right? What's the upper bound's derivative? What's x's derivative? 1. So looks like it's not going to make too much of an impact. So just square root of x squared plus 4. I'm sorry?
What are the one? The one.
Yeah, so the one came from this formula that says P prime of X. P prime of X is saying whatever the upper bound is, take the derivative of that. So what's the derivative of X? So that's why that's there.
Yeah, it's implied to make it like x plus 2.
We can't. Do you know why?
Because it's plus or minus.
It's a plus minus. Now, if it was square root of 4x squared, if everything was multiplied, then yes, then I can break them down. But that plus sign ruins everything. We can't go any further than that. Now, what do you see that has no impact on our answer? That lower bound never shows up. And the reason why is because this lower bound does get involved in the answer, but that lower bound is going to produce a constant, and the derivative of a constant is what? 0. So that's why any constant just zeroes out. It just has no impact because that derivative is going to make it wash out. Okay, part B. The derivative of a depth integral from 3 to x squared of root t minus 1. Okay, let's follow the rule. What do we do with this? We know, again, these two operations cancel each other out. There's no need to do a full integral and full derivative. We just have to jump to what each of those operations will end up doing to the expression. So square root of, yeah, replace the t with the upper bound times 2x. That's it. Okay. Again, the 3 has no impact because we know ultimately the derivative through this process will just wipe it out and make it go to 0. Okay. Part C, derivative integral. It's going to allow us to skip a whole bunch of steps because, why do the process of going there and coming back if we know we're just going to end up in our starting location? Okay, so again, what's going to happen with f of p of x? With the square root, right? Okay, square root of x squared minus 1 times 2x. I just want to prove to you that the bounds have no impact on the answer, right? Everything's the same. The bounds are different, but I'm still getting the same answer. Okay. What's different about part D? Okay, fraction, what else? Okay. My variable is sitting down here, my constant is sitting up here. So I would prefer to get it into this form. So I can change the order of the bounds, but if I change the order of bounds, I'm changing the problem. How can I change it and still make it the same problem? What did we do? What did we learn yesterday? Yeah, I can add a negative, right? I can go from 0 to 3x and then just force a negative into the expression. That way I can match my rule, but yet still not change my overall value of the problem. Okay, so we know these two cancel out. We just have to worry about what the upper bound is going to do to the expression. So what's our answer here? Negative 1 over times 3. If I want to clean it up, I'll get negative 3 over 3x plus 2. Now, what's different about part E? Upper bound and lower bound are both what? Variables. That means they both will leave an imprint on the answer. So if my upper bound and lower bound are variables, I'm going to do the process twice. My upper bound, I'll do exactly what I did before. Make sure there's a minus sign between, and then do the same thing with lower bound that you did with the upper bound. Okay, so let's practice that. So derivative integral, they cancel each other out. We can just work with this 2t plus 3. There's no need to find the full derivative, no need to find the full integral. Okay, so what happens first? 2 times what? Plus 3 times f of p of x times p prime, upper bound's derivative is, what's x squared's derivative? 2x, okay. Minus, I gotta repeat the same process because that x is not a constant, so it's gonna leave something in my answer. Minus what? Parentheses. Times. Okay, if I were to, I'm gonna clean this up here, distribute the 2x through, so I get 4x cubed plus 6x minus 2x minus 3. Guys, turn to page 6C. Added these pages later, so that's why there's like parts A, B, and C here. I do not want to go back and change the pages all over again. So this one has a problem up top. I want to do a different version of it. So if you guys can copy this down here. So what I want us to do is I want us to apply the second theorem that we've just been learning. And then I want to work this out by hand to show you why we get the answer that we get, right? That if we do it the long way, we still get the right answer, but it's longer. And I want to prove to you that this shortcut is much more efficient. And sometimes I feel like students initially are don't know exactly what's happening. So it's nice to see the long version, compare with the shortcut, and actually see, oh, okay, this is why things end up the way they are. So this one, let's do the second theorem first. Second theorem says we know the derivative integral will cancel each other out. I'm going to plug the upper bound in times the upper bound's derivative. So what do we get here? Okay. 2x squared minus 1, okay, times 2x. Right, which we can clean up to be just 4x cubed minus 2x, right? Easy enough, right? Now, let's do this. Let's do the full integral of that expression. Then whatever we get, we'll turn around and take the derivative and see how that produces this answer. Okay. All right, so now I'm going to do it the long way here. So we're going to ignore the bounds, and we're just going to take care of 2t minus 1 to begin with. Okay, what's 2t become? 2t squared over 2 minus, not x, but t. Okay. All right, we'll clean this up here. I get t squared minus t. Okay. I'm going to take care of that integral bounds. Okay. Evaluate it between 3 and x squared. Okay. All right. What do I do with those bounds? Plug in. Okay. So x squared in for t. What do I get? X to the 4th minus. All right. That's my upper bound minus parentheses. 3 squared minus 3. So this is my x to the fourth minus x squared minus 9 plus 3. Or that's just minus 6, right? Okay, so we took care of the antiderivative. Now we're going to turn around and do what? Take the what? Derivative. So I'm going to take the derivative of this expression. So let's do a power rule here. Okay, what's x to the fourth? 4x cubed. What's x squared's derivative? What's the derivative of 9 and 3? 0. Same thing, right? So I want to prove to you that this works. And, for problems that we don't want to go through the whole process of doing this, we can instead just rely on this one. Right? We can only do that if the derivative and integral are canceling each other out. I also want to prove to you, that 3 is not going to show itself in the end. Now, the 3 did show up in this process, but the derivative is going to wipe it out to 0. And that's why we're only left with what that x squared is doing to this problem.
There's
I
no
think,
exceptions to that you were right. You can use it for
I'm sorry.
There's no exceptions to the second theorem, right? You need to play through.
Only the problem is asking for you to undo the process, right? We can't just do this without the problem telling us, oh, there's a opposite operations on top of the same expression. Okay, one last thing here. Let's see if we can do a average value theorem here. This is page 6b. Okay, let's try this one here. Okay, so average value theorem is above here. We're just going to insert everything in. What's my A and B value? Make 2 and 2, yeah. Okay. Now we're just plugging everything in and taking the antiderivative and going through what the formula says. Right. Ignore the bounds, right? Take care of the antiderivative first. So you're basically going from right to left, right? I'm going to ignore the 1/4, ignore the bounds, do the calculus portion first. So whatever the 4 minus x squared looks like between -2 and 2, if I were to look at the curve and average out all the different heights amongst all those points, my average height is going to come out to be 32/3. And now part B is saying, this is the average height of the graph. Find where the graph actually hits that average height, because I can't have an average height without the graph actually hitting that point at some place, right? So basically that's the y value, and we're just trying to figure out what the x value is. So plug 32/3 in for f of x and solve for x. Oh, sorry, 32/3. Oh, sorry, I messed up here. I forgot to do what? I got the I got the integral, but I still got to worry about what? 1/4. Yeah, I forgot about that. Sorry. I took the integral, but I didn't divide by or times 1/4. So 32/12. 8/3. That's part A. Sorry. Thank you. This is one of those instances where we can keep both of our solutions because they both fall inside the interval from -2 to 2. So we're guaranteed at least one solution, but anytime there's more than one solution, we always have to be a little more careful. So, okay, maybe it could fit in, maybe it doesn't, but we got to make sure that that it falls within the interval. If it does, then we can keep multiple solutions. Okay, so check your calendar for your homework. Okay, come get your phones. You don't have to, yeah, you never have to rationalize for this course. You could if you want to, but it's up to you. Oh, yeah, sorry, thanks. Guys, there's gonna be shelter drill during advisement today.
Actually, the also a lot of increase
Oh, do they
on
really?
defense too.
How much time do they have? Oh, they have Sunday?
Yeah, Sunday. I think some people are going back, but some people are not gonna be able to play.
Mm.
Because we were injured for a cancer game. Some people couldn't play, and we got more injuries.
How does Kansas City look?
I think they're pretty healthy. But now, does this be Superman?
He does. He has to carry the team on his shoulders.
That's how we're gonna win. Too. But we have a bad ref, like,
Oh, you don't like the ref?
no, he's he always calls him
Biased?
Build. Yeah,
Oh.
he called a Bills Eagles game, he missed like calls, and if he got him right, then we probably would have won the game. Even though we had many opportunities to that, we missed in that game.
Wasn't there a crew that got suspended because they were just calling terrible games?
Not sure.
Maybe, I don't know if it was recently or. Yeah.
He's like 8-2 when he's calling the Chiefs, like the Chiefs are 8-2. The Bills is 1-3. Is it right there? Hopefully.
Mm-hmm.
Doesn't do that again. I feel like I know that I'm biased when saying this, but I feel like a lot of refs favor the Chiefs. I don't know.
Yeah. Also, they have mainstream appeal too.
Yeah. Oh, we need ratings of reading the Chiefs
Yeah,
game.
right. Yeah, the ratings will be really high for that game for sure. Might be the highest rated game this.
If those
this,
two might be the highest rated division game.
Yeah.
Hope we win. I'll be really
Yeah.
down if we lose again to them.
Yeah.
He's like, I don't think we can't truly beat the Chiefs to be in the postseason. That's right.
Yeah.
Can get our revenge, even though we beat them in the regular season.
I know it doesn't feel the
Doesn't
same.
feel the
Right?
same.
Yeah.
We're not gonna have true revenge till we beat them in the playoffs.
Yeah.
First and second game.
Yeah.
So we're 3-1 against them in the regular season, but then we're 0-2 against them in the playoffs.
Yeah.
Gotta find a way.
Gotta find a way. Have a great day, guys. Thanks.
Thank you, Chief.
Thank you. Xavier, do you have the homework or you show me tomorrow?
Oh, I see.
Okay, show me. Okay, that's fine. Xavier.
Thank you.
Thank you. Thanks, Luke.
Yeah, sorry, on that last one, I accidentally had to use like a lot of whiteout because I was looking at the wrong, I didn't realize that it's.
Oh, okay, that's fine.
Sorry,
Thank you.
but yeah, I finished that one.
Okay, thank you.
In third period.
Thank you.
So locked in. Locked in. Oh, not. Two. First one is good. Well, you did all this. I do. Last night. Work study. Hey, what base you in?
Sorry.
That's all you did. You went through this morning.
This is I got
Oh, Robert, just thanks all. Good luck.
Congrats on being here today.
Oh, thanks. Oh, we got something to put, by the way.
I know you're good again.
Okay, today's the 18th.